Next up, we have another fairly theoretical but also very useful result that's related to the derivative, and this one is referred to as the mean value theorem. And so what we will do in this video, I will kind of give you a visual of what the theorem is saying, give you the formal proof, and then again look at a couple examples that's related to this particular theorem, right? So what I'm going to draw before I state it, so I am going to draw a continuous function on a closed interval, and as usual we're going to call that interval a to b. There's our nice continuous function that's also differentiable. I don't have any sharp corners. Now what I'm going to do is I'm going to draw the secant line that connects the two endpoints, right? So the secant line is right here, right? Now in terms of ordered pairs, so this point is a f of a, and then this point is b f of b, right? So those are the ordered pairs. And essentially what the mean value theorem says is if you have a continuous function on a closed interval and the function is differentiable at every point inside the interval, then there has to be at least one point inside the interval where if I were to draw the tangent line to this curve, it will be parallel to my blue line, my secant line. So just, kind of looking at this here, it probably one point might be over here, and then maybe another point maybe over there slightly, right? So what the theorem is saying is that there has to be at least one of these points somewhere inside the interval between A and B such that the tangent line at that specific point will be parallel to the secant line over the whole interval. In other words, the average rate of change, which is the slope of the secant line, is equal to the instantaneous rate of change at this point and also at this point, right? Now, to give you there's going to be, in the proof, there will be a function, a second function that's defined, and the second function is basically going to measure the distance, this vertical distance between the secant line and the curve itself, right? So that distance there, that distance there. Notice how that vertical distance varies, right? It itself is a function. So depending on my value of x, the difference between the secant and the function will vary, and that particular function I'll give it a name, right? But in order to just so that when I write that particular function down, it doesn't look like, oh, where did that come from? Let me just remind you of what the equation of the secant line is, right? So first, let me write down the slope of the secant. That's our average rate of change. So that's f of b over, or f of b minus f of a over b minus a. And then if I want to find the equation of that blue line, well, since I have the slope and in fact I have 2 points, I'm just going to use the point a, f of a. So the equation of the secant line is this. It's y minus that y value, and then that's equal to, then here is the slope, not a nice expression, but this is the correct slope, and then it's times x minus a. So if I wanted to write this where I've isolated the y, so the equation of the secant, in fact, let me go ahead and call it like S for secant. So the equation of the secant, so S of x, will be all of this, and then I'll add f of a to both sides, right? So I'm just relabeling this as S specifically referring to the secant line. So it's f of b minus f of a over b minus a times the quantity x minus a plus f of a, right? So we are going to make use of this function, right? All right, so let's state what the theorem says, right? Actually, it's a pretty simple theorem when you look at the statement of it. And this is our mean value theorem, often abbreviated MVT. Now, I will say that there are several mean value theorems. This is the one that is giving the relationship between an average rate of change of a function over an interval and the instantaneous rate of change of that function at a specific point, right? So this is the one that's for derivatives, right? And this is what it says. So let f of x be continuous on the interval, again, closed interval a to b, right? And differentiable, right? So, and differentiable in the interval, the open interval now, where we exclude both endpoints a to b, right? And then this is what it says. So then there exists at least one c in the open interval such that if I compute the derivative at that specific point, and that will be equal to my average rate of change over the entire interval, right? So there are lots of geometric ways to interpret this. As I say, this expression on the left is the instantaneous rate of change of my function at a specific point. This is the average rate of change of my function over an interval. And what the mean value theorem is saying, under these two conditions, then there has to be at least one point at which the instantaneous rate of change is equal to the average rate of change over the entire interval. The other way of saying it is that there's at least one point where the slope of the tangent line is equal to the slope of the secant line, right? Okay, so let's take a look at a proof of this theorem, right? Now, so what I'm going to do is write down, so let v of x be the vertical, so I'm just using v for vertical, so let v of x be the vertical, you could say distance or displacement, but the vertical, well, actually let's say displacement, right? Displacement between my curve f of x and my secant line s of x. So between f of x and the secant line s of x. In other words, we're going to define this new function v of x to be equal to, and yeah, let's set our difference up like this. It's going to be my curve minus the line, right? Now, if we think about it, since f is continuous, right? That's continuous and differentiable, and we have a linear function. Now, a linear function is a polynomial. It's a special case of a polynomial. It's a polynomial with degree 1. And we know that polynomials are continuous and differentiable at all values of x. So therefore, this function, v, is going to be both continuous and differentiable on the open interval and in the on the closed interval and in the open interval. So this implies that v of x is continuous on the closed interval and differentiable in the open interval, like this, right? Well, let's actually write down what v of x is. So f of x is just some function, but I do have that equation for the secant line. So let's write that down. So v of x is equal to my f of x minus, and now let's write down the expression for the equation of the secant line. And that was my f of b minus f of a over b minus a times the quantity x minus a, and then plus f of a, right? So what we're saying is now that this function is continuous and differentiable. Now, what's interesting is if I were to evaluate this function at the endpoints. So let's take v of a. Well, let's see what we will get. We would have f of a minus, and then square brackets, I'd have all of this. This is my slope of the secant. And then in parentheses here, I would have a minus a, because I'm simply, wherever there's an x, I'm just plugging in a. So I'd have a minus a, and then here I would have f of a. Now, because this is a minus a, this whole term here is 0. And then what do we have left? We have f of a minus f of a. So that's 0. And this actually makes sense geometrically, because we're saying that the secant line and the curve passes through that point a f of a. So the vertical distance between them, or displacement between them, would have to be 0 at that point. But let's look at what happens at the other endpoint as well. So f of b would be now f of b minus, so wherever there's an x, we're going to plug in b, right? So what do we have here? Now, again, this coefficient here is just a slope, right? It's just the slope of the secant line, so that stays there. And then for this x, let's replace it with b. So I'll have b minus a there, and then I'll have plus f of a there. But look at what happens. Now, I have b minus a and I have b minus a. So this fraction is reduced. Now, what are we left with? Well, I have f of b, and then if I distribute this negative sign, this becomes negative f of b, and then this negative and this negative makes it plus f of a, and then this negative and this positive makes it a minus f of a. And again, at the other endpoint, again, that vertical displacement is equal to 0. Now, what is the point of doing this? Well, let's think about it. We have a function that's continuous on a closed interval, differentiable on the open interval, and the function value at the endpoints are equal. That sounds to me like a recipe for Raleigh's theorem. So Raleigh's theorem applies, right? So therefore, Raleigh's theorem applies to this v of x, right, on this interval. And what does Raleigh's theorem says? It says if you have a continuous function on the closed interval that's differentiable in the open interval, and the function value at the endpoints are the same, then there has to be at least one value inside the open interval a to b where the derivative of this function is equal to 0. It has to have a stationary point, right? So this implies v prime of x must be, well, actually, let me write it like this. So v prime of c must be equal to 0 for at least one c that's inside this interval, right? Well, let's see if we can write down the derivative of this. Now, again, don't overly complicate it, but so v prime of x. Well, taking the derivative of this will give me f prime. I'll bring down the minus. Now, the thing is, this is simply a number, right? This is just a number that's multiplying this linear function. If I differentiate a linear function, all I'm going to be left with is its slope. I'm just going to be left with the coefficient of x. The coefficient of x is this part. So I'll have f of b minus f of a all over b minus a. Essentially, this becomes a 1. In fact, let me write that in. And this is just a constant. There's no x here, so its derivative is 0. So therefore, again, let me clean this up. The derivative of this vertical displacement is equal to f prime of x minus this quantity f of b minus f of a over b minus a. So now let's apply Raleigh's theorem. Says that there has to be at least one value c such that this derivative is equal to 0. So applying Raleigh's theorem, what do we get? V prime of c, which is, again, if I substitute now c in here, I'll have f prime of c minus f of b minus f of a over b minus a. That has to be equal to 0. And then solving this for f prime of c, so therefore f prime of c, adding this quantity to both sides, it just changes that minus to a plus, and then we'll have exactly what our mean value theorem says. Right? So there has to be at least one c, right, where the instantaneous rate of change at that value c is equal to your average rate of change over the entire interval. And that's our QED. All right? So that's our mean value theorem. Let's take a look and see, what sort of questions, and we'll do a couple questions similar to this. Let's take a look. So example. So does the mean value theorem apply to this function? F of x equals the natural log of 2x on the interval, and let's say my interval is from 1 to e, right? And let's say explain, right? Because we have to be able to explain why it is or why it does or doesn't apply. And then if so, find, not final, that looks like a AL instead of a D. So find all values guaranteed by the mean value theorem. All right. Okay, so the thing for the mean value theorem is we have to establish continuity and differentiability. Now, this is a logarithmic function, right? And what we know about logarithmic functions is, so logarithmic functions are going to be continuous whenever the quote-unquote inner function is positive, and it's also going to be differentiable, again, whenever the inner function is positive. So since f of x is equal to the ln of 2x, f of x is both continuous and differentiable whenever 2x is greater than 0, right? So as long as I have something positive inside the ln, then it will always be continuous, always be differentiable. Now solving this inequality is very easy. Divide both sides by 2, so you get that x must be greater than 0. So, and this is fine. So on this interval, right? So for all values of x, so when x is in this interval, it certainly satisfies this property, right? So the MVT applies to our function f of x equals the natural log of 2x, all right? So we know it works. Now we want to find, okay, where is this special value of x or special values? So where is the derivative of this function, in other words, the instantaneous rate of change of this function, equal to the average rate of change of this function on this interval? Well, let's go ahead and compute. Let's start with the average rate of change. So let's compute f of e minus f of 1 over e minus 1, right? So we have to plug e into this function, so this will be the natural log of 2e minus the natural log of 2, and then this is all over e minus 1. Now, there are a couple things we can do to simplify this. What I will do is use a property of logs that allow me to combine these two logarithms into one. Since I'm taking a difference of these logarithms, I can write this as the log of 2e divided by 2, and then in the denominator I'll still have e minus 1. So what happens is the 2's cancel, and I'm left with the natural log of e, which is equal, or I'm sorry, over e minus 1. And the natural log of e is equal to 1. So this is the average rate of change of this function over this interval. Well, what is the instantaneous rate of change? Well, that's the derivative. So f prime of x, let's now compute the derivative of this using our rule for natural logarithms as well as the chain rule, because we have this composite where it's the ln composed with the 2x. So it's 1 over 2x times 2, so that comes out to be 1 over x, right? So where are these two things equal? Well, that's pretty easy to see. So where is f prime of x equal to f of e minus f of 1 over e minus 1? That's what the theorem says. Well, there has to be a point. So take your derivative and set it equal to our average rate of change. But again, this is easy to see that therefore x has to be e minus 1, right? So this So if you want to go ahead and use the letter C, you can. So therefore C, the special point, is e minus 1. So what does this mean? Well, if you sketch the graph of the function, and remember our interval here is from 1 to e, basically your log function looks something like this, right? And then e minus 1 is going to be somewhere in this interval. So let me mark that off specially. Let's say e minus 1. So if I put, yeah, in fact, let me go ahead mark that off in green. So the secant line will look like this, and then the tangent line at my point that I've indicated in green will look like this, right? And they would be parallel, right? So this line here has slope, well, the slope at this point would be 1 over e minus 1, right? So the slope of the red line there, so the slope of the tangent is 1 over e minus 1, and the slope of the secant is also like what we found earlier. So the slope of the secant is also 1 over e minus 1. So at that special point, the tangent line is parallel to the secant line, which means the instantaneous rate of change at that point is equal to the average rate of change over the entire interval. And that's what's guaranteed by our mean value theorem as long as our conditions are met. All right? So there you go, another somewhat theoretical way of using the derivative, but I guarantee you this is something that you will see in future courses, and I look forward to that moment, and also look forward to the next video. See you then.